Good morning everyone, we are Group 7 and today we are presenting our design project for ECH 3125 Heat and Mass Transfer Process. Our project focuses on the comprehensive design of a shell and a tube heat exchanger specifically engineered for a chemical process involving chlorinated hydrocarbon. Before we dive into the technicalities, I'd like to introduce our team. The members of the Group 7 are FATIN AFIQAH, NAVYA ANANTHAN, INTAN NABILA and CHARLENE. Together, we manage the thermal calculation, material selection and safety integration for this project.
The overview of today's presentation slides include design specification, working principles, purpose of heat exchanger, shell and tube configuration, Excel parameter, assumption and calculation, AutoCAD design, design challenger and conclusion.
This slide shows the design specification of our shell and tube heat exchanger. The process stream consists of chlorinated hydrocarbons such as chlorine, hydrochloric acid, benzene and dichlorobenzene isomers. This mixture needs to be heated safely before further processing. The operating temperature of the process stream increases from 40 degrees Celsius to 55 degrees Celsius, while hot water flows from 80 degrees Celsius to 60 degrees Celsius as the heating medium. The mass flow rate of the process stream is 0.1745 kg per second and the required heat duty is 3.588 kilowatts. The main objective of this design is to develop a shell and tube heat exchanger that can efficiently and safely heat the chlorinated hydrocarbon mixture to the desired temperature. Next, I will continue to explain the working principle of the shell and tube heat exchanger. First, convection heat transfer. It occurs when the cold process stream flows through the shell side while the hot water flows inside the tubes. Heat transfer depends on the convection heat transfer coefficient or known as H. Next is conduction heat transfer. It takes place through the tube's wall. Heat flows across the tube material according to Fourier's law, and this depends on the tube thickness and material used. All these heat transfer mechanisms are combined into the overall heat transfer coefficient, which includes thermal resistance and fouling factors to represent real operating conditions. For the design method, we use both the NTU method and the LMTD method to analyze and size the heat exchanger accurately. The purpose of this heat exchanger can be divided into three main aspects. First is the process condition. The heat exchanger increases the process temperature from 40 degrees Celsius to 55 degrees Celsius, preparing the stream for downstream operations such as separation, compression, and also storage. The second one is safety management. Controlled heating helps minimize corrosion caused by HCl and chlorine, prevents thermal decomposition reactions, and reduces vapor pressure for safer handling. Lastly is energy recovery. The system transfers 3.588 kilowatts of thermal energy using hot water with only a 50 degrees Celsius temperature drop, ensuring efficient energy use while maintaining standard heating system parameters.
This covers our selected shell and tube heat exchanger design, organized into 4 specification categories. First, the shell side uses a one-pass configuration and counter current flow to heat the process stream from 40 to 50 degrees Celsius. Second, the tube side features a fixed tube sheet with triangular pitch and 32 tubes to cool hot water from 80 to 60 degrees Celsius. Third, material selection includes copper-nickel tubes, stainless steel tube sheets, and a carbon steel shell with corrosion allowance. Fourth, key dimensions include 15.836 meters of tube length using DN25 schedule, 40 pipe, ensuring efficient heat transfer and reliable operation for industrial applications.
The parameters of this shell and tube include heat flow rate, which is 3588 joule per second. The mass flow rate is 0.745 kilojoule per second. The specific heat capacity of water, the temperature hot in and the temperature hot out, which is 80 and 60 respectively, and the temperature cold in and the temperature cold out, which is 40 and 50 respectively. The volumetric flow rate is 0.000174 meter cube per second. And then there is the fouling factor, which is for the inside, which is the hot water. The value is 0.002, and the outside is the mixed substance, which is 0.004. And for the mixed solution, assuming all mixed solution calculation using properties of water, which is at 40 degrees Celsius, the parameters are density, dynamic viscosity, thermal conductivity, the Prandtl number, kinematic viscosity, velocity, Prandtl number surrounding, velocity max, outer diameter, inner diameter, length. The assumptions for the calculation are it is a steady state operation, no change in system conditions over time. Changes in kinetic and potential energies of fluid streams are negligible. Negligible heat losses to surroundings, uniform fluid properties within each stream, no phase change in either fluid, sensible heat transfer only, fouling resistance are given as constants. The thermal resistance is included and calculated based on tube dimensions.
For the essay calculation, the first step we find the CP mix and mass flow rate of water. Then we find C min and C max to find the smallest C. And then you find Q max and Q to find the effectiveness of the heat transfer. Then to find NTU, then we got 1.002. The next step is calculate the HO and HI. The HO that we got is 5587.78 and HI is 1877.24. Then we use both to find the U. Then we got 180.87 and the length we got is 15.83 meters, and the tube that we need is 32 tubes. Then the T cold out is 55 degrees Celsius.
This is our AutoCAD design with front and side view. And as labeled, number 1 is tube inlet, second tube outlet, third shell inlet, fourth shell outlet, fifth tubes, sixth shell, and 7 is tube sheets.
For the features of heat exchanger, the first is it's a shell and tube heat exchanger and it has a one shell pass design for simplicity and effective heating. The tube material that has been used is the stainless steel 316 liter. And the for the thermal performance aspect, the duty is 3.59 kilowatt. The effectiveness is 0.5. The hot side is the water from 80 degrees Celsius, which cools down to 60 degrees Celsius, and the cold side is the organic compound, which is the mixed compound, which is the at 40 degrees Celsius and heats up to 55 degrees Celsius. For the operational features, it includes compact and scalable layout, low fouling design with smooth tubes, safe temperature and pressure operation, easily cleanable tube bundle.
Material selection was the major challenge due to the compressive nature of the fluid. We selected the copper nickel Cu90/10 for the tube. Why? It's offer high thermal conductivity for a compact design and naturally inhibit the growth of the algae and bacteria. For corrosive resistant, it forms a protective oxidized film, which is the vital in the oxygen-rich environment that might otherwise cause pitting. We also recommend a U-tube configuration to allow for easier mechanical cleaning and descaling. To optimize energy, we focus on 3 areas. The first, temperature, utilizing AI-driven thermostat to prevent thermal overshoot. Second, flow, maintaining a tube side water velocity sweet spot between 1.2 and 2.4 meter per second to prevent fouling while ensuring high heat transfer. Lastly, fouling, we integrate a precise fouling factor as a safety margin and suggest nano coating on water side surface to prevent mineral build-up. Safety is our final pillar. Our design include pressure containment compliance with ASME Section 8 and pressure relief valve on both sides. Second, leak prevention, the use of the double wall heat exchanger and keeping the process fluid at a higher pressure than the water. The lastly is smart monitoring, high precision temperature transmitter and accelerometer to detect flow-induced vibration before they cause failure. In conclusion, this design safely and efficiently meet all process requirements for the hydrocarbon mixture.
In conclusion, a shell and tube exchanger was successfully designed that effectively raises the temperature of a process stream from 40 degrees Celsius to 50 degrees Celsius using hot water at 80 degrees Celsius, which cools down during the heating process. Using the NTU effectiveness method, the design was validated through manual calculation, simulation and AutoCAD schematics, resulting in effectiveness of 0.5 and giving 32 tubes as an end result. The exchanger is energy efficient, safe and practical for industrial use, meeting all thermal and operational requirements while integrating core heat transfer principles. Through this analysis, the final design ensures reliable performance under specific conditions, promotes sustainability through effective heat recovery, and aligns with practical engineering standards for real-world implementation.
This is all the reference that we use in this project. That's all from us. Thank you.